Hi children, hi all. Welcome, warm welcome to another chemistry class. See, in this class, we are discussing some of the excellent questions from the chapter Chemical Bonding and Molecular Structure. That is the fourth chapter. Okay, are you ready? Can we start straight away? Yes. The first question. The decreasing order of stability of O2, O2 minus, O2 plus and O2 2 minus. You know the stability depends on the bond order and the molecular orbital electronic configuration. And if you keep in your mind what is the orbital electronic configuration, MO configuration of O2, you can easily find out. O2 configuration, how it comes. Try to memorize. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2p z2, pi 2p x1, x2, pi 2p y2 same. And the ending is pi star 2p x1, pi star 2p y1. That is the electronic configuration ending for O2. And thereby we get a bond order 2 for O2. So bond order for O2 is 2. What about O2 minus? One more electron comes. There is an additional electron coming for O2 minus when compared to O2. And where that additional electron goes, it is going to destabilizing orbital, anti-bonding molecular orbital. You see, what is the last configuration? Pi star 2, pi star 2px1, pi star 2py1. So the next electron will go to pi star orbital. An electron entering into pi star orbital will destabilize the molecule. And thereby the bond order decreases for each electron. Bond order decreases by half. You have been taught in the class. So O2 bond order 2 becomes O2 minus bond order 1.5. Right? What about O2 plus? One electron decreases. One electron decreases. There the bond order will increase because the electrons are removed from pi star orbital. So bond order 2 for O2 becomes 2.5. Right? And what about O2 2 minus? O2 2 minus is even less stable than O2 minus. So here the bond order is 2. Here the bond order is 1.5. Here the bond order is 2.5 and here the bond order is 1. You have been taught or you have studied in the class and hence the order. What is the order coming? Third choice it must be. You see, this is the configuration for O2 and I am talking about this one. Pi star 2px1, pi star 2py1 and hence the bond order you are getting 2. Now O2 minus 1 electron will be additional coming here. Therefore bond order decreases from 2 to 1.5. While here an electron is decreasing from this area. Therefore bond order increases 2.5. And O2 2 minus, this is even less stable than this because one more electron coming in the pi star orbital and the bond order becomes 1. So which is bond order minimum? O2 2 minus, that is minimum stable. We are talking about stability. O2 2 minus is minimum stable. Then it is O2 minus. Then it is O2. Then it is O2 plus. And if it is O2 2 plus available, that will be most stable. Bond order 3. So order of stability of oxygen species you have learned in the increasing order O2 2 minus, O2 minus, O2, O2 plus, O2 2 plus. It is accordingly the electrons being added and removed based on pi star orbital. You know, anti-bonding electrons when decreases, bond order increases. When anti-bonding electron when increases, bond order decreases. When bonding electron increases, bond order increases. When bonding electron decreases, bond order decreases. You've been taught in the classes, right? On to next question. Not isostructural. The species not isostructural. You know these are isostructural. Both are sp3 hybridized, pyramidal in shape. XeF4, XeO4, they are not isostructural. They are not isostructural. XeF4, how many pair of electron? 8 plus 4, 12. There is 6 pair of electron, and that is sp3d2 hybridization. And you know that it is square planar geometry. It is square planar geometry with the 2 lone pairs. Now, what about XeO4? XeO4, there are 8 valence electrons, so the pair is 4 pair and go for sp3 hybridization. So it is Xe 1, 2, 3, 4. This is XeO4. This is XeO4 and it is tetrahedral. They are not isostructural. One is square planar and the other is tetrahedral. Right? What about the others? Both are tetrahedral. What about others? That is diamond and silicon carbide. They are making dangling bond sp3 hybridized tetrahedral network structure. Okay, next. Correct geometry and hybridization. Just now we have discussed. Just now we have discussed XeF4. It is sp3d2 hybridization. sp3d2 hybridization and square planar geometry. The molecular shape is square planar sp3d2 hybridization and the molecule is AB4E2 type. AB4E2 type. 4 bond pair, 2 lone pairs. Next. Wrong statement. SeF4, CH4, same shape. That is wrong. That is the wrong statement. SeF4 and CH4. CH4 is tetrahedral sp3 hybridization. What about SeF4? The very famous molecule I'm sure you practiced. SeF4. 6 valence electron. 4 surrounding atom, so there is 10 electrons, 5 pair. It is sp3d hybridization and it will be selenium 1, 2, 3, 4, 5 and it is F and a lone pair. Hope you understand the shape. Seesaw shape. Seesaw shape. CH4 is tetrahedral shape. So it is not same shape. What about others? I3 plus bend geometry. Yes, it is AB2E type molecule, bend geometry. AB2E or AB2E2. What about I3 plus? It is I2 plus. So it is 7 plus 2, 9 minus 1, 8, 4 electron pair. It is sp3 type. So it is AB2E2 type. It is AB2E2 bend shape. PH5, BiCl5 do not exist. You know, it's a true statement. PH5 does not exist. And regarding bismuth, only stable +5 state is with the fluorine, BiF5. P-pi D-pi bonds present in SO2. Yes, in SO2 there is P-pi D-pi bond. As sulfur contain sulfur in the +4 state, you know, sulfur in the +4 state, it will be d orbitals involved. Sulfur in the +4 state means excited. So you can see there is one d orbital. You see this in SO2, this d orbital is involving P-pi D-pi. It is undergoing sp2 hybridization. So sp2 hybridization. So this p electron and this d electron involved in pi bonding. So this one pi bond formed by P-pi and the other pi bond formed by P-pi D-pi. And the d orbital involved is this one. Right? If so, what is happening in SO3? Check it out. If so, see, this is sulfur +4 state. This is sulfur +4 state. 1, 2, 3, 4 unpaired electron. What about in SO3 where it is +6 state? Verify. Next, NO2 plus, NO3 minus, NH4 plus. NO2 plus is valence electron 5 minus 1, 2, sorry 4 by 2, so it is 2 electron pair, sp hybridization. NO3 minus, so 6, therefore 3 electron pair, that is sp2 hybridization, and this is the very famous sp3 hybridization. So it is sp, sp2, sp3, sp, sp2, sp3, first choice. NO2 plus is sp linear, NO2 minus is sp2 bend shape, and NH4 plus is sp3 tetrahedral. Next, isoelectronic, isostructural. You see, sulfur in the third period, nitrogen second period cannot be isoelectronic. This can be isoelectronic. This can be isoelectronic. And this cannot be isoelectronic. Chlorine third period, carbon in the second period cannot be isoelectronic. Now left with the 2 and 3. Left with the 2 and 3. You see, carbonate is trigonal planar, sp2 trigonal planar. What about NO2 minus? What about NO2 minus? It is sp2 bend shape. sp2 bend shape. And the answer is second choice. Second choice. ClO3 minus sp3. ClO3 minus. It is sp3 with a lone pair. What about SO3 minus? SO3 minus is also sp3. SO3 minus is also sp3. Both are pyramidal shape. Both are sp3 hybridization, pyramidal shape, isoelectronic, isostructural. You see, you have to maintain isoelectronic, isostructural. It is isoelectronic as well as isostructural. Right? Next. Shape and hybridization of I3 minus. Shape and hybridization of I3 minus you have learnt. It is I2 minus 7 valence electron plus 2 monovalent atom 9. 7 plus 2 9 plus 1 5, 10. So it is 5 electron pairs. It will go for sp3d hybridization. Hope you know how to find the hybridization. Valence electron of central atom surrounding monovalent atoms, charge of the anion, you are getting 10 by 2, you are getting 5. 5 stands for sp3d. That is what 5. sp3d. That's how to find out the hybridization simply. So it is sp3d hybridization. sp3d hybridization, and it is linear. sp3d hybridization, you have iodine 1 2 3 4 5. You will have one iodine here, one iodine here, and 3 lone pairs here, and it is I3 minus linear molecule. And the question is, choice is option 4, sp3d linear shape. sp3d linear shape. The species having bond angle 120 degree, 120 degree, what doubt? Option 4, sp2 trigonal planar, BCl3, the very famous molecule, sp2 trigonal planar, 120 degree. While that is pyramidal, this is pyramidal, that is bend T shape. ClF3 is sp3d hybridization, bend T shape. Answer is fourth choice. Same bond order, same bond order. Isoelectronic species can maintain same bond order. You see, carbon, nitrogen minus option 3, Cn minus, it is bond order 3, and CO bond order 3. That is the answer. That is the answer. While the bond order you can work out NO, bond order is 2.5, NO plus bond order is 3. Write the configuration of N2 itself. Write the configuration of N2 itself and verify what is the bond order of NO. How many electrons? 15 electrons. Write down. And NO plus, how many electrons? 1 electron decreases, and how the bond order comes. So evaluate the bond order NO 2.5, NO plus 3. You can easily find out. And the same bond order coming, it is in option 3, Cn minus and CO. While N2 bond order you know 3 and O2 minus we have already discussed, O2 we have discussed. Next. Number of lone pair of electrons in the central atom, ClF3, just now I told you, ClF3. How to find the hybridization again? ClF3, 7 valence electron, 3 surrounding monovalent atom by 2. You are getting 5. That is sp3d hybridization. It is chlorine 1, 2, 3, 4, 5. It is bend T shape due to the presence of lone pair of electron. Chlorine contain 2 lone pair of electron. Chlorine contain 2 lone pair of electron. Answer is option 2. There are 2 lone pair of electrons. Option 2. And now there can be a question, how many lone pair of electrons in the molecule? You have to be careful, because there is fluorine, no? Because there is fluorine. Each fluorine contains 3 electron pairs. So there are 3 fluorine, 3 into 3, 9. And chlorine 2. Totally 11 electron pairs as a whole in the molecule. But here it is pretty clear. In the central chlorine atom is asked. Central chlorine atom is asked. Okay, next. Highest bond order. Highest bond order. Highest bond order is 3. 3 bond order 3, option 2. Bond order 3, option 2. That contain bond order 3. While Cn plus you can work out bond order 2, because 1 electron decreases from the bonding molecular orbital. Verify that. And NO already commented. Cn, it is 2.5. So write the configuration of nitrogen itself. You know 15 electron up to nitrogen, small molecules, nitrogen 1 configuration, oxygen and above 1 another configuration. Taught in the class, you have learned that the molecular orbital configurations. Of course, if you deal with the CO plus and all, for CO you have to be pretty careful, because there can be a small variation in CO configuration, because the bond length observed for CO and CO plus, CO is bond order 3 and CO plus is 3.5. You may go wrong if you are writing nitrogen configuration. That has to be pretty careful. Yes. Only pi bond according to molecular orbital. Only pi bond according to molecular orbital. That's a very famous example. The hypothetical species C2 will have only pi bond. C2 will have only pi bond. You may try the electronic configuration for C2. C2, 12 electrons it is. Sigma 1s2, sigma star 1s2, you know, sigma 2s2, sigma star 2s2. What next? Pi 2px, pi 2py. According to nitrogen configuration, there are 12 electrons, 2, 4, 8, 10. Carbon 6 into 2, 12 electron, 2, 4, 6, 8, 9, 10. That is the configuration. That is the configuration, right? But that configuration is written for oxygen, right? It is for oxygen. So the configuration I have written wrongly. The configuration is to be, this has to be inverted, right? This has to be inverted. It is nitrogen configuration. It is nitrogen configuration. So it will be sigma 2s2 sigma star 2s2 pi 2px pi 2py and sigma 2pz. That is the configuration for carbon. So 12 electron, 2, 4, 6, 8, 10, 12. This is the configuration for carbon, which otherwise, suppose I have written, it was better I have written the other configuration also. Suppose if you write the configuration for oxygen, hope you remember what I have written earlier, which I erased. There are unpaired electrons, and C2 would have been paramagnetic. Actually, C2 is diamagnetic. It is only this configuration will fit for C2, because C2 originally is diamagnetic. Suppose if we have written it the other way like oxygen, it will be paramagnetic, which is against, which is not true. So this is the configuration of carbon. And when you try to find the bond order, you see this pair get cancelled, this pair get cancelled, and the bond order here it is in the bonding molecular orbital. There are 4 electrons. So it is 4, no anti-bonding electron, 4 minus 0 by 2, you are getting 2, and the bond order is CC, double bond. Bond order is CC, double bond, and both the bonds are pi bonds. Both the bonds are pi bonds. You see here, both the electrons are pi electron, and both the bonds are pi bonds. Check what if happens in case of B2. Find out. B2, what is happening? Find out. Boron 2. Hope you understood. Next. Matching the column. Already we had a talk. XeF4 is square planar. We had a talk. So A with the 2. A with the 2. So these two choices out. XeF6 is distorted octahedron. XeF6 is distorted octahedron, and it is 3. B with the 3. And C, XeOF4. XeOF4. 8 valence electron, 4 surrounding monovalent atom by 2. You are getting 6. That is sp3d2 hybridization. Therefore, the molecule will be like this. Xenon 1, 2, 3, 4, 5, 6. There are 4 fluorine surrounding and 1 oxygen top, 1 lone pair. It is square pyramidal. It is square pyramidal geometry. So this will go for square pyramidal. C with the 4, and the answer is first choice. And XeO3 is coming like this. XeO3 1, 2, 3. It is pyramidal in shape. It is pyramidal in shape. XeO3, it is 1. Hence the answer first choice. Hope you understand how I calculated and found the structures. You have to practice more on that area. Yes. Next. Incorrect statement about PCl5. Two axial PCl5 bond make 180° with each other. Yes, correct. That is a correct statement. Axial PCl bonds are longer. Yes. PCl bonds, axial bonds are more elongated. PCl5 molecule is non-reactive. This is incorrect. PCl5 molecule is reactive because it contains 3 planar bond, shorter bond, and 2 axial bond, elongated bond, and that axial bonds are unstable. Hope you understand. So it is third choice. 3 equatorial PCl bond make 120. So that is also correct statement. Next one. Dipole moment 0. Here it is not 0 because chlorine cis position. So it will go for a polarity this direction and go for a polarity in that direction, not 0. And this is 0. This is 0. Thereby you can have chlorine in this direction and this direction mutually cancelled. And this is also 0 because chlorine opposite, and the answer is B and C. Option E, B and C. That is the correct answer. Nitrogen atom sp3 hybridization. Here it is sp3, you know, pyramidal. This is sp3 tetrahedral, you know, and this is also sp3 hydrazine. That is also sp3 hydrazine. You see that nitrogen, hydrogen, and connected to nitrogen and one lone pair, and that is connected to two hydrogen and a lone pair. You see it is sp3 hybridized. 1, 2, 3, 4 electron pair, sp3 hybridized, hydrazine, NH2OH, that is also the same. NH2OH hydroxylamine, that is also sp3 hybridization. Answer is all. All are sp3 hybridized. All are sp3 hybridized. Next. Maximum number of lone pairs on central atom. SCl4. We worked out earlier. SeCl4. SeCl4, SCl4 same. It is seesaw shape. Earlier we have worked out sp3 dehybridization. Seesaw shape. One lone pair. It is AB4E type. Seesaw shape. One lone pair. So here it is one lone pair. This we have worked out, sp3 dehybridization, 3 lone pair, linear molecule. Few minutes back we have seen sp3 dehybridization, AB2E3 type, AB2E3 type. So this molecule is AB4E type and this molecule is AB2E3 type. What about this? This is sp3D2 hybridization and this molecule is AB4E2 type. So 2 lone pairs. And what about this? This we have worked out earlier. sp3 hybridization. sp3 hybridization. And the molecule is AB2E2 type. 2 lone pair. So the answer is B. There are maximum number of lone pairs in second choice and all the molecules we have already worked out. Okay. Next. CO bond order in carbonate. CO bond order in carbonate. This is carbonate. This is carbonate. Here there is a double bond. Here there is single bond. So what is the bond order? Bond order is the average because this is a resonance molecule. A molecule undergoing resonance, the bond parameters will go for average. So what is the bond order? Here there is a double bond. So 2 bond, 3 bond, 4 bond. Take the total count. 2, 3, 4. So it is 4 bond shared by 3 oxygen. So it is 4 by 3. So it is 4 by 3. 4 bond. 2 bond here, 1 bond here, 1 bond here. 4 bond shared by 3 oxygen atom. 4 by 3. Option D. Option D is the correct answer. Next question. A tetraatomic covalent molecule AB3 has a definite dipole moment. The sigma bonding orbital used by A and shape of the molecule will be most probably AB3. AB3. sp2 cannot be pyramidal. sp2 cannot be pyramidal. Out. sp3 pyramidal. That is the answer. sp3 pyramidal. You have AB3E type. This is having a dipole moment like ammonia. This is having a dipole moment like ammonia. And now sp linear. sp cannot be AB3. AB3 cannot be sp. sp3 tetrahedral. Tetrahedral cannot be AB3. Tetrahedral means AB4. and then the dipole moment is 0. It is AB3 only, so it cannot be tetrahedral. Answer is option B. Dipole moment of NF3 0.24, ammonia 1.46. The difference is due to the difference in. Difference is due to the difference in the direction of polarization. In NF3, the polarity is towards fluorine. And in NH3, the polarity is towards nitrogen. So that makes a difference. So NH3, if you take, there is a lone pair, and NF3 you take, it is clearly explained in the textbook. Always the polarity of lone pair is away from the central atom. This is always away from the central atom. Now here, hydrogen, so the polarity is in this direction. Now you see all polarity in the one direction. While here being fluorine, this is in the opposite direction. So here the net dipole moment will be in this direction. Here the net moment will be 1 to up and all the 3 to down. So the net dipole moment will be towards down. So there will be some sort of cancellation here. 1 up, 3 down. There will be some sort of cancellation. So the dipole moment is somewhat getting cancelled. So it is basically due to difference in the direction of polarization as we have fluorine coming. Hydrogen and fluorine. That is the difference. Next. And this point I am sure you have seen in the textbook. Percentage ionic character of bond having 1.275 Armstrong, its length, and 1.03 dBi, its dipole moment will be. You know how to find the percentage ionic character. How to find the percentage ionic character? It is percentage ionic character is equal to mu observed by mu maximum into 100. What is mu observed? 1.03 dBi. 1.03 into 10 raised to 18 ESU centimeter in CGS into 100 divided by mu maximum. What is mu maximum? Mu maximum will be charge maximum into distance. What is the charge maximum? 4.8 into 10 power minus 10 ESU into bond length 1.275 into 10 power minus 8 centimeter. I have explained everything in CGS system. If you want, you can work out in SI, no problem. If you want, you can work out in SI. Anyway, this gets cancelled and you get 1.03 into 100 divided by 4.8 into 1.27. 4.8 into 1.27. So it is 103 by somewhat 6. 100 by 5 is 20. 100 by 6 is less than 20. The answer could be option D. As we have seen, option D will be the answer. Now the entire things you can do in SI system also. You see how to do in SI system. You will get the same answer. Same answer. Percentage ionic character. It is observed dipole moment. Observed dipole moment 1.03 dBi into 3.3 into 10 power minus 30 coulomb meter into 100 divided by mu maximum, charge maximum into distance. What is the maximum charge? One charge. 1.6 into 10 power minus 19 coulomb into 1.275 Armstrong into 10 power minus 10 will take you to the same answer. Both are same. One is CGS system, one is SI system. Finding percentage ionic character doesn't go to make any difference whether you change the unit or not. So 1 unit electric charge, this much coulomb and this much electrostatic unit. 1 dBi converted to like this in SI system. 1 dBi is 10 power minus 18 ESU centimeter in CGS. That's all. You might have taught everything in the class concerned to this. Anyway, percentage ionic character, how do you calculate? It is the observed dipole moment divided by The maximum possible polarity into 100. Next. Number of nodal plane in pi star orbital. Pi star orbital, all of you know. Pi star orbital. Pi star molecular orbital. How you get pi star molecular orbital? Pi orbital means, suppose we are taking p orbital undergoing pi configuration. It may be addition or subtraction. Addition will take you to pi mo. Suppose it is 2px, 2px. Suppose it is undergoing addition, it will be sigma 2px. How is it getting sigma 2px? This is the nuclear area and you get it like this. These two are getting added. That is addition interference. This is sigma, sorry, this is pi 2px. Now, there is another one. This is bonding molecular orbital. What about the other one? Subtraction. Anti-bonding molecular orbital. These are getting subtracted. So, this and this getting subtracted means what will happen? Subtracted means what will happen? This is the nuclear center and the orbital will be lying like this. The lobes will be lying like this. There will be repulsive interaction. This is attractive interaction. Here it is repulsive interaction. And this is pi star 2px. One is stabilizing, one is destabilizing. So here how many nodes are there? That is a question. Here how many nodes are there? Here you have one nodal plane. Here you have one nodal plane like this, one nodal plane like this. There are two nodal planes. There are two nodal planes. In that case, option A is the correct answer. Pi star orbital will have two nodal plane, while pi orbital will have one nodal plane. This is additive and this is subtractive. This is constructive, this is destructive. This is stabilizing, this is destabilizing. This is lower energy, this is higher energy. All of you know that. Electron added here will stabilize the molecule. Electron added here will destabilize the molecule. That's it. A. Next. Which has a net dipole moment. This is tetrahedral symmetric molecule. No net dipole moment. SO2 is the answer. SO2 is bend shape. SO2 is bend shape. And that is having net dipole moment. Here, this is not having net dipole moment, planar. This is tetrahedral, no net dipole moment. Answer is SO2. Next. Number of pi bond in the molecule. Tetracyanoethylene. Tetracyanoethylene. You know tetracyanoethylene. This is tetracyanoethylene molecule. This is tetracyanoethylene. Oh, there is a small mistake. This is double bond. This is double bond. So how many pi bond? Here you have one pi bond, one sigma bond. Here you have one pi bond, two pi bond. Here you have two pi bond. Here you have two pi bond. Here you have two pi bond. So it is 9 pi bonds. All of you know when there is one bond, it is sigma bond. When multiple bond, one sigma, other is pi. So when there is a triple bond, one sigma, two pi. Option D. Next. BF3 combines with the NS3 giving BF3NS3. BF3, all of you know, this is BF3. This is BF3 and it is sp2 planar and it is interacting with the NH3 and this is sp3 pyramidal. And now they are going to interact. All of you know this is electron rich system, this is electron deficient system. There will be a coordinate bond formed like this and the system turn like this. BF3 is interacting with the NH3. Now you can see there is a change in the central atom. Here sp2 boron, here it becomes sp3. sp2 planar boron becomes sp3 tetrahedral. Now sp3 pyramidal nitrogen becomes, of course, no change in the hybridization. It is sp3, but it is pyramidal becoming tetrahedral. So the hybridization and shape of boron changes, while the hybridization of nitrogen does not change, but the shape changes. So this and this change. sp2 becomes sp3, planar becomes tetrahedral. sp3 is sp3, pyramidal becomes tetrahedral. So what is the answer? Boron changes hybridization from sp2 to sp3. Yes, that is the correct answer. That is the correct answer. What about the others? Nitrogen changes, wrong. Both boron, nitrogen, wrong. Both boron, nitrogen change, wrong. A is the correct answer. Hope it is clear. A is the correct answer. Next one. Hybridization of nitrogen atom in piperidine or piperidine. Piperidine. sp3, sp3. Look at the nitrogen center. It is making one bond, another bond, hydrogen, and a lone pair. So it is 1, 2, 3, 4. So it is sp3. AB3 E-type system. Same thing. Next. The species C2 has effectively, just now we have discussed, 2 pi bond. C2 with the configuration we have a discussion. It is 2 pi bonds. And this is the reason. 2 pi bonds. Next. Number of hydrogen bond present in one plane around a given water molecule in ICs. See, around one water molecule, there can be how many water molecules? H, O, H. How many water molecules can be hydrogen bonded? That is a question number 1. How many hydrogen bonds can be, how many bonds hydrogen water molecules can be? One can be here, and one can be here, and these two will be in one plane. These two will be in one plane. While this lone pair, it is something standing like this. This is tetrahedral system, right? So this two bond pair and this lone pair, and they are not in the same plane. They are in vertical planes. And you see that lone pair will be interacting for hydrogen bonding. This lone pair will be interacting for hydrogen bonding, and this water molecule and this water molecule are available in the mutually perpendicular plane. That two water molecule in one plane, these two water molecule in one plane. Totally there are 4 water molecules surrounding water, and the two water molecules will be in different plane. If one is in the horizontal plane, the other will be in the vertical plane. Okay. Next. So what is the answer? Number of hydrogen bonds present in one plane. Option B. Next. The repulsive interaction in the order. Very simple. Lone pair interaction maximum. Then lone pair, bond pair. Then bond pair. Option A. Option A. Which has intramolecular hydrogen bonding? Orthonitrophenol. In orthonitrophenol, there is intramolecular hydrogen bonding as they are coming at immediate position. This is ortho. This is phenol. And this is orthonitrophenol, which make a hydrogen bonding and is intramolecular hydrogen bonding. And due to intramolecular hydrogen bonding, orthonitrophenol is more volatile than paranitrophenol. Orthonitrophenol is more volatile than paranitrophenol and the boiling point decreases. And it is separated by steam distillation. Right? So due to intramolecular hydrogen bonding, the intermolecular attraction decreases. Therefore, it becomes more volatile. Next, while meta para, there is no intramolecular hydrogen bonding. Meta para, there is no intramolecular hydrogen bonding because they are far from the position. They are unable to make a intramolecular hydrogen bonding. Rather, there is intermolecular hydrogen bonding. So that's a very important point you are learning in the last portion of that chapter. Intramolecular hydrogen bonding, intermolecular hydrogen bonding. In paranitrophenol, there is intermolecular hydrogen bonding. In orthonitrophenol, there is intramolecular hydrogen bonding. Right? And that was the last question from the chapter. So that too was a pretty typical type of questions what we have discussed from the chapter. So we will meet in another class with another set of questions from a different chapter. Okay, children, hope you have gone through. It will be useful to you. Definitely. We will meet in another class. Okay, bye. See you.